Welcome to the third part of this uh, surface chemistry lecture series. So today we'll be discussing about the chemistry of colloid, which is a very important topic. I'll try to cover the preparation, purities, that is purification of colloid, and how these colloids they exhibit certain properties. So before entering into this topic, we have to compare the three important types of solution. That is the true solution, colloidal solution, and suspension. So shall we get into the topic? Are you ready? You please take down notes. Okay? Right. Before explaining about the preparation of colloids, I'd like to compare the properties of a true solution, colloids, and suspension so that we can understand better about the preparation and properties of colloids. With regard to the size of the dispersed particle, that is, in the case of true solution, it is called a solute. In the case of colloidal solution, we call it dispersed phase, as well as in suspension, it is called a suspended particle. So when we compare the suspended particle or dispersed particle or the solute particle, or we can say the smaller portion of the solution. In the case of true solution, the size is almost less than 1 micrometer, 1 millimicrometer. And in this case, it is ranging from 1 millimicron to 1 micron. And in this case, it is more than a micron. When I say millimicron, milli means 10 power minus 3 and micron is 10 power minus 6. So it is 10 power minus 9. Okay. So 10 power minus 9 means it is less than the nanometer. Whereas in the case of colloidal solution, it ranges from nanometer to micron. But in case of suspension, the suspended particle, the size of the suspended particle will be more than 1 micron, that is more than 10 power minus 6 meter. So based on that, you may arrive at some visualization also. If it is more than a micron means probably that is you can see the suspended particles with the naked eye. And this is very difficult in the case of true solution. You cannot see the solute particles once it is dissolved. But in the case of colloidal solution, with the help of microscope, an effective microscope, we can actually see the particles, the colloidal particles, that is the suspended, the dispersed particles will be moving here and there. With regard to the diffusion, so when diffusion means that there is spreading. So the diffusion through animal membrane, because of its very fine size of the particles, they diffuse very rapidly, like a filtration, is it not? In the case of colloidal solution, it diffuses slowly because the particle size is somewhat bigger than that of true solution. In the case of suspension, it will not diffuse at all because of big size. Let us consider the settling of particles. True solution will not settle once it's thoroughly mixed. But in the case of colloidal solution, usually it will not settle by gravity but settles by centrifugation. For example, the blood serums can be centrifugated. So you can see the that is the yellow part, the RBC, separately by the centrifugation. And especially in the case of suspension, it settles down even by gravity. Filterability. So when we talk about the property filterability, this cannot be so easily filtered because everything goes into that. And in the case of colloidal solution also, you have to use very sophisticated filtering equipment. Otherwise, you cannot filter it. But suspended particles like precipitate, that can be filtered. For example, when you form silver chloride precipitate, that can be filtered out easily as a precipitate using the filter paper. Then, filtration with the ultra filter. With the help of ultra filter, even with the help of ultra filter, it would be very difficult to separate the solute from the solvent. But in the case of colloidal solution, the dispersed particles, the dispersed phase can be filtered from dispersion medium using some ultrafiltration technique. And as usual, this can be normally filtered by a normal filtration itself. Then, as far as appearance is concerned, the solution is transparent, almost clear. But in the case of colloidal solution, it won't be so clear, it will be slightly turbid. But in this case, this is opaque, almost blocking. It is not at all transparent. When you consider once again the silver chloride precipitate like a curd, that is, it is opaque almost. Then, nature. So, homogeneous by mixture. You cannot find any distinct particles dispersed. Whereas in the case of colloid and suspension, you can see almost the heterogeneous. Physically, they are distinct. Then this is called Tyndall effect. Tyndall effect is nothing but the scattering of light when it passes through the solution. In the case of true solution, it won't because that is the particle size is so less, so very small. So it cannot that is scatter. But in the case of colloidal solution, you can have scattering of light. This is called the optical property of Tyndall effect. Optical property of colloidal solution, it is called Tyndall effect, light scattering. Then, in this case, it will also show Tyndall effect, obviously, because the size is bigger, is it not? Right. Then, when we talk about the number of molecules in a particle, this particle in single molecule or ion, it is available. But here, it will be an aggregate of few hundred molecules. But in the case of suspension, the particle is aggregate of millions of molecules. It will be bulky. Okay, so these are the important differences as far as properties are concerned among the true solution, colloidal solution, and suspension. Now let us move to the preparation of colloids. With regard to the preparation of colloids, there are three important methods: chemical methods, physical disintegration or Briggs arc method, peptidization method. In the case of first one, chemical method. In chemical method, that is, already, that is true solution is very, very small. Is it not? True solution is very small. The solute particle is very small. And colloidal solution is somewhat bigger and suspended solution is somewhat much bigger. So the technique is from true solution, which is very small, you can convert into what? Colloidal solution, that is by chemical method. You understand this? So this is the first technique, by chemical method. In the second method, that is, we are making the smaller sized solute particles into a bigger one, which is matching with the colloidal solution. Do you understand? Right. So this is A to B. And in the case of electrical disintegration or Briggs arc method, we break the precipitate, okay, into colloidal solution. Okay, so we are breaking by somewhat an electrical method called Briggs method. We'll be explaining about that. Okay, so this is C to B technique. So this one is A to B, and this one is C to B. Okay, so peptidization method is a unique method. We'll be explaining about this one also. Now let us move with chemical methods. In the case of chemical methods, see, that is, you have got the arsenic oxide by passing hydrogen sulfide, there will be a double decomposition, and thereby you are able to get arsenic sulfide as a colloidal sol. So arsenic oxide and hydrogen sulfide being a gas, and this is a solution. Okay, so it is converted into what? So this is the true solution actually. This is true solution. Okay, but this becomes colloidal solution. Do you understand? I hope now you should be able to understand how we convert the true solution into colloidal solution by decomposition method. Do you understand? And when sulfur dioxide you have got and the hydrogen sulfide, when they subjected to oxidation, then sulfur sol is obtained. Okay, and similarly ferric chloride or auric chloride, gold. So by treating with formaldehyde with water, it subjected to reduction, it undergoes reduction. So auric chloride, it is in the form of Au3 plus oxidation state. So this oxidation state, auric chloride, becomes what? Au0. So this is reduction. Okay, so you can write down the reduction process like this: Au3 plus the combination of 3 electrons to give Au0. So you are able to get gold sol with the zero oxidation state. Okay, then, and formaldehyde is subjected to oxidation in this case. So it oxidizes this one, but this reduces and this gets oxidized. Okay, so formaldehyde becomes a formic acid. That is the oxidation. Whereas this is electronation, is it not? Auric Au3, this is electronation means what? Reduction. Okay, do you understand this one? Whereas HCHO here, HCHO that undergoes oxidation to become formic acid. So this is a redox reaction. Okay, right. Then ferric chloride, when it is hydrolyzing, it gives ferric hydroxide. Okay, sol, ferric hydroxide, sol is obtained. Ferric chloride is a neat true solution, whereas this one is a precipitate, like not precipitate, a colloidal dispersion. Precipitate is suspension. Please make a note of it. Okay, right. Now let us move to the next method called Bredick's arc method. In this method, that is, you have got cathode and anode. Okay, so you have got cathode and anode. So when the solution is subjected to the electrolysis, okay, so electrolytically what? So this is possible. So we are breaking this. We are breaking the suspended particles. We are breaking actually the suspended particles into what? The colloidal particle. Okay. So this is known as uh, Bredick's arc method. So you can see here we have got the electrodes, plus and minus electrode, and you have got the dispersion medium, and it should be done because that is, it should be done under cold conditions. So we have put some ice cubes also. Otherwise, it will generate heat, and if it generates heat, once again the colloidal particle forms will be broken. So to avoid that one, that is, we are maintaining this at a cold temperature. Okay, so the intense, otherwise the intense heat produced vaporizes the metal itself. Okay, so in this way, that is, we can convert the metals like gold, silver, platinum, etc. into their colloidal solution. Okay, right. Next, the next process is this is artwork done by Pavani. Thank you, Pavani, for your good work. Then, peptization. The peptization, this involves a process of converting the precipitate into the colloidal solution. As I already mentioned, this is C to B technique. Okay, the bigger particle is converted into the smaller particle. Okay, so this is also C to B. Okay, C to B. So this is electrically done and this is chemically done. That is the difference. Okay. Then, so process of converting a precipitate into a colloidal solution. Okay. Then by this can be done by shaking with some dispersion medium in the presence of some small amount of electrolyte, and that electrolyte like a sodium chloride, So this is called the peptizing agent. Okay. So what happens is when the precipitate when it is agitated in presence of sodium chloride, So these ions are absorbed on the surface of the precipitate, and they help to break up into smaller colloidal particles, so that there will be lot of surface activity. Okay, so this is with regard to the preparation of what? The colloidal solution. Okay. Purification of colloidal solutions. So we have seen the different methods of preparation of colloids. After preparing the colloids, it should be properly purified. The process of reducing the amount of purities is called purification of colloidal solution. So we have three methods: dialysis, electrodialysis, ultrafiltration. Let us see one by one. Dialysis. So our student Akash has drawn this diagram very nicely. Thank you, Akash. See, in dialysis, the dissolved substances from the colloidal solution is removed. That is by means of diffusion through a semi-permeable membrane, through a membrane, a suitable membrane. Usually, true solution can pass through the animal membrane, but not colloidal particles. So there are some special kind of membranes like animal membrane. We can make use of this parchment paper as well as a cellophane sheet for arresting the entry of the colloidal particles. So we make use of this technique. Now what we do is we have to get ready with a bag which is made up of dialyzing membrane that is kept inside the flowing water, a vessel containing a trough containing a flowing water, a fresh water is allowed inside. So what happens? These water solvent molecules will be washing through all the suspended particles, small ions and molecules. They diffuse through the membrane because of the fresh water. Then the pure colloid is left inside the bag. So thereby we can purify the colloidal solution. So this is a normal process, but it's a slow process. So in order to expedite, we can influence the dialysis by introducing electric field so that the ions migrate out to the oppositely charged electrodes, leaving the pure colloid inside the bag. So this is another technique, that is electrodialysis. Okay, you please go through this. Then filtration, ultrafiltration. Normal filter paper allows colloidal particles, but filter paper with the impregnated colloidal solution, this is called colloidal solution, does not allow colloidal particles. So we make use of this technique. So we need to separate the colloidal particles from solvent and soluble solute. So we make a special filter that is called ultra filter paper. First of all, let us explain what is colloidal solution. This is 4% nitrocellulose in alcohol ether mixture. So a normal filter paper is impregnated with that, and it is further hardened by using formaldehyde. And finally that filter paper is dried. so that you've got a special ultrafilter paper where the colloidal particles are filtered out. And this is a very slow process. So using vacuum, we can increase the speed of ultrafiltration. So what are the different methods of purification of colloidal solution? Dialysis, electrodialysis, and ultrafiltration. And within that, we can apply vacuum also. So it is vacuum ultrafiltration or ultrafiltration under reduced pressure. Okay. Now let us get into the topic properties of colloidal solution. There are seven important properties of colloidal solution. One is colligative property. Second, Tyndall effect. Third, color. Fourth, Brownian movement. Fifth, electrophoresis. Charge. charge on colloidal particles, charge on colloidal particles, then electrophoresis, and finally precipitation or coagulation. We'll discuss one by one. We know what colligative properties are. Colligative properties depends on the amount of the solute present as far as true solution is concerned. For instance, let me consider boiling point. So the boiling point of water gets elevated by adding small amount of solute. When we increase the solute, the amount of solute, the elevation of boiling point also increases. So what are colligative properties? Elevation of boiling point, depression of freezing point, increase of phosphatic pressure, and a relative lowering of vapor pressure. So it's obvious that as far as a true solution is concerned, the colligative property depends on the number of solute particles. But let us consider what is the situation in the case of dispersion of colloidal particles. Since the dispersed phase, the dispersed colloidal particles are size-wise, it is bigger than the solute in the true solution, is it not? So there will be less number of equal concentration. Therefore, the colligative property value will be lower than that of the true solution with the solute with the same concentration. So do you understand this? Right. Secondly, we need to discuss the Tyndall effect. Tyndall effect is nothing but the scattering of light by colloidal particles. So our friend Gokul has done a wonderful artwork here. So we have the colloidal solution here. So in this colloidal solution, light is passed through this, and we convert this by using a convex lens. So when it is passed through the colloidal solution, and you can find the scattering of light. That's called scattering of light. Okay, so this scattering phenomenon can be very well observed, especially under the microscope. Okay, so this light scattering effect of colloidal dispersion is called Tyndall effect. Okay, right. And this is the Tyndall comb. Okay, then the dust particles visible in projection in cinema theater, so that is because of Tyndall effect. And you can see the sun rays passing through the dense forest also. We can find the dusty, that is a sunbeam. So that dust beam, the beam containing the dust particles through the dense forest or jungle, that is also Tyndall effect. Now, what are the conditions for the exhibition of this Tyndall effect? First of all, the diameter of the dispersed particles should be smaller because it should be scattered, is it not? So it should be smaller than the wavelength of the incident light. Okay, then the refractive index. What is refractive index? That is represented by mu, is it not? We call it mu. So we call it a sine of angle of incidence divided by sine of angle of refraction. Okay, right. So this refractive index of the dispersed phase and the dispersed medium should differ greatly. So their respective refractive indices should be wider. So should be wider in the difference. Okay, so that we can realize the Tyndall effect more effectively. Okay, right. Now let me move to the color. As far as color is concerned, so the color exhibited by a particular colloidal solution depends on the wavelength of the light scattered. The wavelength depends on size and nature of the particle. That's very important. Okay. Then, in fact, the color of milk appears blue by reflected light. So, in what view we uh, watch the color, so that also depends. When you look at the transmitted light, it appears red. When you look at the color of the milk, it appears blue by reflected light. Okay, so when the light is passed, either the light is reflected or transmitted. So when you look at the transmitted angle, then it appears red. When you look from this side, it appears blue. Okay, so it depends on the viewer's angle also. So as far as colloidal solution colors are concerned. Okay, so this is somewhat a unique behavior of colloidal particles. Next, Brownian movement. This Brownian movement, that is, Google has wonderfully that is drawn this Brownian movement as zigzag movement. See this? It goes like this. It goes like this, but wherever it goes, that is, it adopts a linear motion. Okay, that you should remember. So this zigzag continuous motion is called the continuous motion of the dispersed phase in the dispersion medium of colloidal solution is called Brownian movement. This is due to the unbalanced bombardment of particles of the molecules of the dispersion medium. See, that is, whenever the dispersed phase is there, there will be a dispersion medium also. After all, it is a present. This dispersed particles are present in the dispersion medium. So they will be surrounding each and every dispersed phase, is it not? So that will bombard the what do you call the dispersed phase, and it is because of that this dispersed phase will be moving. The dispersed particles will be moving constantly. Okay, then this speed is inverse. This speed of the moment is inversely proportional to the size of the particles. When the size is less, the speed increases. When the viscosity of the solution is less, the speed increases. Okay, right. But it does not depend on the nature of the colloid. However, the Brownian movement does not allow the particle to settle down, and thereby it supports the stability of sols, is it not? So this is one of the positive factor of this Brownian movement. So it supports the stability of sol. Then let us get into the next one, that is charge on colloidal particles. This is a very important one. So colloidal particles, they generally carry electric charge. It can be either positive or negative. Due to electron capture, they got this capabilities. Okay, so it is a kind of what do you call that is this electric charges can be explained by various theories. One is by electron capture, another is by selective absorption, and the third one by formation of electrical double layer. Let me look into the first one, that is electron capture, but that is not acceptable in by certain authors. So let us go to the next one, which is having a better evidences also. That is called a selective adsorption. The selective adsorption means, let me take, we have potassium iodide solution. When we add silver nitrate in excess potassium iodide solution, what happens? Silver iodide forms. Along with that, the iodide anions, they are captured, they are absorbed over this silver iodide, and thereby it forms a negatively charged colloidal particle. Do you understand this? Next, sometimes let us take the reverse of this process. Silver nitrate. Let us take silver nitrate and in excess, then we are adding potassium iodide. What happens? Silver iodide once again forms. Now in this case, silver plus ion is absorbed. They are absorbed all over the silver iodide. Okay, so thereby they result positively charged colloidal particles. Do you understand this? Right. But Now let us go to the formation of electrical double layer. So in this case, what happens, So that is, you would have formed this AgI, okay, AgI bar I bar. That is, silver iodide is solvated, surrounded by this iodide anions, okay. And immediately the potassium from the solution, no, they will be surrounding this uh, and thereby it forms what I call a double layer. Okay, and similarly, when we take silver iodide and that is surrounded by Ag plus in the first layer, immediately a second layer is surrounding that Ag plus, and that is iodide layer. Okay, right. And I can get one more example also. For example, when you take hot water and add ferric chloride, what happens? That is hydrated X moles, maybe hydrated ferric oxide forms, and that is formed along with the adsorption of ferric ions. So these ferric ions will be surrounding the hydrated ferric oxide. Okay, so thereby it attains what charge? Positive charge. So they are positively charged colloidal particle. And similarly, when you take sodium hydroxide and where we add ferric chloride, then it forms hydrated ferric oxide with the hydroxyl anion adsorbed over that, and thereby it results, that is anionic colloidal particle. Do you understand? And as I already mentioned, that is, let us consider this one. It forms a double layer because of the counter ion. Okay. Now let me explain this double layer, and this is known as the Helmholtz electrical double layer. See, that is, we have got this AgI over which iodide are adsorbed, iodide ions are absorbed, and thereby it forms a negative what? The first layer. Immediately it forms a positively charged, that is oppositely charged second layer. And this is somewhat stronger, whereas this will be mobile. This is fixed, this is mobile. This fixed layer, okay, this fixed layer and the is strong, whereas this is a mobile layer. This will be diffusing. This is not so strong. This is diffusing, and thereby it moves here and there. Okay, so such type of a difference in the potential there arises, uh, a potential difference, and that potential is called electrokinetic potential, that is known as zeta potential. So it's a very famous theory called the zeta potential, zeta electrical double layer. Okay, so and let me go further into this topic. The presence of equal and similar charges on colloidal particles imparts repulsive repulsive forces among the charges. Okay, so let me consider a colloidal sphere like this. Okay, so what happens? It is surrounded by, as I already told you, some specific charge. Now another colloidal particle, it is surrounded by the negative charge. Definitely there will be a repulsion, is it not? And thereby it helps what? Coagulation. That is aggregating, not coagulating, aggregating. So aggregating or coalescing. Coalescing means that is approaching each other. So thereby, because in their proximity they can interact, So when they interact, it may collapse. So this charged surrounding the colloidal particles help in what? The aggregating or coalescing in the proximity, and thereby it improves the stability of the colloidal solution. So this is a very important point to be noted down. Okay, right. Next, electrophoresis. Electrophoresis, that is, we discuss about the electrophores, the charged colloidal particles are called generally electrophores. So the movement, the migration of charged colloidal particles under the influence of electric potential is called electrophoresis. Okay. Now, the cataphores are the positively charged because they are moving towards cathode. Anaphores, they are moving towards anode. So they are called, that is anaphores. So you can observe here. So this electrophoresis is a very important property among the properties of colloids. Coagulation or precipitation. The process of settling colloidal particles is called coagulation. The settling tendency, that is called coagulation, and it can also be called precipitation. It means what? From the colloidal state to it becomes what? Precipitate, a bigger one, a suspension, by merging, by that is coalescence, we said, is it not? So the stability of a lyophobic means what? That is oil loving. It means hydrophilic, is it not? So water loving. So the stability of a lyophobic salts is due to the presence of charge because they are charged. Okay. If the charge is removed from the particles, they come nearer to each other and forms aggregation of these particles that results a coagulation, and thereby they settle under the force of gravity. Okay. Then, so there are some methods of coagulation of lyophobic, that is hydrophilic salts. First, by introducing the electrophores, is it not? So, electrophoresis, by applying some electric field oppositely charged ions, okay? Then, by mixing oppositely charged charged salts so that it can be neutralized, and then boiling. When we boil, what happens? It is a, I mean, the charged spheres are disturbed. Then we have to do the persistent dialysis also, and by addition of electrolytes, this is possible. Now let me take this point: addition of electrolyte. When we add electrolyte, what happens? That is coagulation takes place. For instance, this is known as the Hardy-Schulze rule. That is, greater the valency of the fluctuating ion, more will be the precipitation. The fluctuating power of coagulating negative salts is in the order of aluminium 3 plus, Ba2 plus, Na plus. Means aluminium 3 plus is greater than that of Ba2 plus, and that is greater than Na plus. Similarly, the fluctuating power of coagulating positive salts, like in this case, that is, we have FeCN 6 times. What is this? FeCN, hexacyanoferrate, is it not? Hexacyanoferrate. And similarly, this one is, this is a tetravalent ion. You have to note down that tetravalent ion. And what about this? This is phosphate, is it not? So phosphate. And what is the valency of phosphate? The valency of phosphate is 3 minus, is it not? 3. And what about the sulfate anion? The sulfate anion is divalent, that is 2 minus, is it not? And then you know something about chloride, and that is monovalent. Okay, so that is monovalent, right? So based on the valency, I think you are able to understand the fluctuating power of the coagulating positive salts getting increased. Okay, so here 4 valency has more fluctuating power than trivalency, thereby bivalency and monovalency. What is coagulating value? It is nothing but the minimum concentration, that is in terms of millimole per liter of an electrolyte to cause precipitation. Okay, so how this coagulation results? By, that is a movement, bringing the colloidal particles together. Okay, so thereby it becomes a precipitate. Okay, so the next one is coagulation of lyophilic. When I say lyophilic, it is water hating, hydrophobic, is it not? So such type of salts, they have generally better stability due to two important factors: because of charge and solvation, and that too can be coagulated by adding electrolyte and by adding suitable solvent. Okay, and then finally, protection of colloids. The lyophilic are more stable. The lyophilic salts are more stable than lyophobic salts. They are extensively solvated, particularly the lyophilic salts are extensively solvated. What do you mean by solvated? Solvation, surrounding of solvent molecule. Okay, so the molecules will be surrounding to a greater extent around the lyophilic colloidal particles. The lyophilic salts protect. It is a very good characteristics of a lyophilic. It protects the lyophobic salts also by surrounding them. So when we want to protect the lyophobic, we can add lyophilic so that it acts as a protective colloid. Okay. So with this, that is, we are able to complete this very good chemistry of colloid, but due to lack of time, that is, we have to move to the next part tomorrow, and that is the emulsion. And we have got some more applications in colloidal chemistry also. So we will discuss about emulsion, and followed by that, we will try to complete this wonderful lesson. Okay. Thank you very much for watching this video.